Okay. I think, let's see if we have more bodies coming in. I think we do. I think we do. Okay, so very good. Okay, so this is we've been talking here about word embeddings and graph embeddings. That's been kind of the theme of the first two talks. And after seeing where we got last time and thinking about infrastructure, I think what I'm going to do in this last session is we're going to continue talking a little bit about graph embeddings and graph representation learning. That's kind of the fancy name for the field these days. And then I'm going to talk about one of the ways that I use embeddings a lot, which is in kind of what I'll call nearest neighbor methods for machine learning and and just data science, understanding data sets. That's going to be kind of my vision. First of all, any questions or comments from people who were here before? I see I've got a lot of. Let me go through the same thing we did earlier. Who's been to a previous session? Who's still here? Okay, that's good. And who has not been to a previous session? Okay, that's good. And who was at a previous session but not here now? And that, again, still seems to be right. Okay, so I think this is going to be fine. I understand this. I think this will, if you're new here, I don't think there's going to be anything that's so overwhelming. If so, don't be afraid to ask. So, okay. So what I want to talk here about is we're talking about this idea of how do we represent basically the nodes of graphs by numerical vectors that sort of low-dimensional numerical vectors so that you can do machine learning on them. If you build models using linear regression, what do you want? You want numbers coming in as features, so you can build a classifier or a predictor. You can use each of the dimensions of an embedding as one of these variables. So once you have this, it's easy to build a regression model for your particular application or any other machine learning thing that takes a bunch of numbers in to try to make a prediction. And we started talking about, at the end last time, this idea of building representations of graphs that change. And, we talked, again, about many techniques. If you missed this part, the previous work, maybe it'll be a little mysterious, but not that much. The goal here is we want to come up with a short vector to represent each node in a network, say a person in a social network, in a world where things change. Some people get angry and unfriend somebody, okay? Sometimes people make friends. Hopefully people make more friends than they unfriend, but you can kind of imagine a world that these networks change. People join them, meaning that you need a representation for them now which you didn't have before. How can you build some kind of representation that is somewhat dynamic? Okay, it's changing to what the graphs are. And one way to do it is to simply run the graph embedding algorithms that we talked about every once in a while on the current graph that you have. Maybe every month Facebook goes and does another deep walk of their entire graph and comes up with a new embedding for this. The good thing about this is it's up to date within a month. The bad thing about that is that the dimensions of, when you train one of these representations, these dimensions are kind of implicit, latent dimensions, and they don't have names, they're not comparable with independently trained things. So either you have to do something to bring the dimensions into alignment, which we talked about earlier, or you have to retrain your entire model from scratch every month, and maybe that's not a bad thing. But these are issues to keep in mind. And again, one problem with doing the time slicing approach is that building graph embeddings are reasonably expensive operations. Not ungodly expensive operations, but reasonably expensive operations. So in my lab, we regularly build embeddings on graphs with 1 million nodes. But that would take typically a day or so of training on a reasonably big single server, okay? So let's say, I think of it in terms of this number comes from my student who's trying to make it big. If we have a GPU, a CPU with 40 cores, okay, it took us 100 hours to embed a 2 million node graph. That either seems like a lot of time or a little time, depending upon who you are. If you're Facebook and you've got 1 billion computers at your disposal, you say, I just parallelize it, okay? If you're the guy in the lab, you say, I can't run this on every time slice of my graph because, it just takes a long time. We talked about faster ways of doing graph embeddings, things like these random projection methods. And maybe they're good. They're not quite as good as the more time-consuming embeddings that we talked about. But that may be one solution to these kinds of problems. And let's just move on. Now, in my lab, there is another approach to building embeddings for dynamic graphs that I want to just hint at a little bit. I'm not trying to turn you into, I guess, try to sell you on our method. But it does have some interesting ideas that if you're trying to come up with a representation for what graphs are, that are kind of interesting. And let's just see if I can do this. This was stolen from my student. What if we were in I told you about our application before, where we would like to be able to read the entire network of changes to Wikipedia and see if we can figure out when is it that a node changed a person, let's say, changed its role in the network, okay, changed its role in the world. We have examples of people who were movie stars and businessmen who became important politicians. You could kind of imagine if you went along and looked at every edit to the Wikipedia graph as you go along. You would have, how many people are there in Wikipedia? There are a few million people, I think. These days, it's probably about, let's say, 2 million-ish people in Wikipedia who have pages in the English Wikipedia edition. So that, so that's a lot, okay? And If we would like to monitor whether somebody's network has changed, the number of edits in terms of insertions of links and deletions of links in Wikipedia over 20 years of Wikipedia is measured in the billions, okay? So how can we build something that's going to kind of monitor as we go along, okay, for entities, when have they moved? Again, I'm interested in when has somebody's embedding position moved enough to say, hey, this is probably different, something has changed, okay? So one problem we tried, I sent this to my students, and what happened, first of all, they complained to me that there's too many people in Wikipedia, okay? And you would like to be able to, 2 million, a graph with 2 million nodes is a big graph. Most of them are not going to change. Would there be a way to embed some subset of the nodes that we care about and monitor how they change? So let's think about it. Wikipedia has 2 million nodes, okay? Maybe there are 1,000 interesting figures we care about, okay? Is it possible that maybe we could just build an embedding on just the figures we care about instead of the whole node graph? Can I get the idea that I want? I have a big graph. I want to use the big graph, but I don't want to build a representation for every node in my big graph, because building it for every node is going to be expensive. Everybody get that idea, or any questions about that? Now, this may seem weird, but how could this work? Because in some sense, if I want to build a representation of Donald Trump, let's say, it would seemingly depend upon all the other people that Donald Trump is connected to. Okay, and there are, I'm not going to want to build representations of all of these people. Okay, so how can we build take advantage of the whole graph while building representations for only a small number of people, a small number of nodes, okay, such that these representations will be comparable, okay? And the approach that we came up with is kind of interesting, and we'll talk about it. First, we build something called personal PageRank vectors for each one of the people that we care about. Okay, and I'll tell you what PageRank, you may have heard the word PageRank somewhere along the line. You may wonder what personal page, well, I'll talk about that in a second. So what we're going to do is to take the graph, build these PageRank vectors on each individual person we care about, and then compress them using some kind of technique to a lower number of dimensions, okay? And we use some hashing technique, that's not important, okay? So what is, with this approach, what is personal PageRank, and what is a PageRank vector? First of all, what is PageRank? Okay, PageRank is if you're going to be working with networks, and many of you were working with networks as of a few hours ago. Maybe you've given up after hearing my talk earlier, but I assume most of you are still working on networks, okay? Or many of you are still working on network data. PageRank is a computation that says if I go on a graph and I do a random walk for an arbitrary number of steps, what is the probability that I end up at each vertex? Okay? Now, what's interesting about this? Okay, well, first of all, a vertex that you end up with high probability is probably a more important vertex than one that you end up with low probability. Okay, that's kind of the idea behind PageRank. It was originally developed kind of by Google. It was kind of the fundamental thing to tell, is a website important or a website unimportant? If you go to Wikipedia's website, there's a high probability if you did a random walk on the internet, you end up on Wikipedia's site. If you do a random walk on the internet, there's a low probability you end up on Skeena's homepage. That means that Wikipedia is more important than Skeena's homepage. That's kind of the idea What is the computation for PageRank? Well, you could do it maybe by simulating random walks and just counting how many times I end up at each vertex. That would be one way to estimate the probability of ending up at every vertex. There is a linear algebra way of looking at it, which is more interesting, which says that the PageRank of a vertex at the jth iteration is the probability of being at vertex v at time j is going to be the sum of all neighbors of v. If I have a vertex u that's a neighbor of v, what was the probability I was at vertex u at a time j minus 1, the previous step? And if once I'm at vertex u, the probability of me jumping to v depends upon the degree of vertex v. If there's 5 places I should jump, I should get 1/5 of that probability. And this iterative method lets you estimate the probability, it gives you the probability of ending up at each vertex at time j. In practice, this quickly converges, and in practice there is some linear algebra magic to make this run reasonably fast, so that's why PageRank is a good thing. Any questions? And if you've never played with PageRank and you do have an interesting network, it's something I encourage you to go and compute on your network. What is the centrality? What is the PageRank for all the vertices in your network? And it does a surprisingly good job of identifying who the most important, what the most important nodes were. When we ran it on PageRank, on Wikipedia's graph, and we took a look at who were the most important people that had the highest PageRank on Wikipedia, okay? We had it, this was done a few years ago. It was a US President Bush, Napoleon. People know who Napoleon is, right? Jesus, I bet you've heard of him, okay? President Obama, things like this. Who here has heard of Carl Linnaeus? Does anyone know Carl Linnaeus? One person in here, people in here. Notice one Scandinavian. I don't know if that's suggestive. I don't know where he's from, but that sounds, is he Scandinavian or? Okay, so that's why. Who was Carl Linnaeus? Carl Linnaeus was the one who developed the classification system for taxonomy for plants and animals and things like that. You've probably heard of the Linnaean system. Maybe that means something. So what happened? Every plant or animal, their Wikipedia page said, Carl Linnaeus told us what our name was, okay? All those pages were a vote on how important Carl Linnaeus was. If you don't want plants and animals voting on who the most important people are, you could build a network of just people pages. And when you do that, Linnaeus didn't do it quite as well. Any questions about this idea of centrality? And that this is a good isolated feature for every vertex, okay, in a network. Any questions about PageRank? Why it's a good thing? Okay? Okay, good. And, but there's some engineering decisions that on your network that depend upon whether or not you're, to make your PageRank computation good. Suppose you have a vertex that has an out degree 0. There's no way to get out from you, okay? What's going to happen to the probability, or maybe the only link from you is to yourself. That's even better, okay? What's going to happen? The moment you get stuck in this vertex, future walks are not going to let you get out, right? You can only accumulate more and more probability with time, right? Eventually, this node that has no outlinks except to itself would look like the most popular, most important node in the network, right? And that would be bad. So you got to watch out what you're dealing with self loops, okay? You've got to remove things that don't go anywhere. You also have to allow random jumps. So in practice, what you would like to do is to avoid getting stuck someplace. You'd like to go to one of your neighbors, okay, and then with some probability go to someplace else in the graph, like teleport out, okay? And this is necessary to get a good, to avoid some of these troubles of getting caught in weird subgraphs that are designed to catch you in things. Any questions about that? So if you're Google and you're worrying about these graphs and people are trying to design the links in their network to maximize their rank, you've got to do various tricks to try to fight them. If your data was not designed in an evil way, maybe it's less important. But any questions about that? Okay, so PageRank is a good thing. Now, now I understand what my student did. I took some slides from one of my students, and now I'm understanding that it's a little liver than I thought it was. There's another idea, though, from this, once you understand PageRank. Remember I was talking about personal PageRank? What does the personal PageRank have to do with something? What if, in starting from a vertex, okay, in global PageRank, I'm saying if I do a random walk over the entire graph, what's the probability I end up with in any, at every vertex? Personal PageRank says, if I do random walks from a particular node, what's the likelihood I end up at every other vertex? If I do long enough walks, then probably this converges to the global thing. But if I'm doing short walks from me in a social network, who am I going to be visiting? I'm going to be visiting my friends. I'm going to be visiting my friends' friends, things like that, right? And friends of mine who I'm pretty close to, maybe there's a lot of different paths to, I'm more likely to end up on that. So personalized PageRank is the idea that you center it around a particular node, which is the one you care about. You do walks that are short or of some interest. And whenever you do one of these jump things, remember I said you should be able to, in real PageRank, randomly jump to some arbitrary vertex just to get out of a trap. Now with personal PageRank, you want to jump back to the home node every once in a while to get back into the trap. That's kind of what the thing is. The personal PageRank is to try to determine how important are nodes to you, okay, in the graph. Does everybody kind of get that idea? So if you do a personal PageRank walk, okay, around a particular node, what are you going to get? Again, these are things that, actually, let's go back here. Sorry about this. Now I'm understanding what my problem was. What's going to happen here, okay, you're now going to, for each person in this network, you're going to go do a personalized PageRank vector. That means what? You're going to determine the probability that if you do random walks around me, what's the likelihood you're going to end up at different nodes, right? And this is going to look different. If you do a random walk around Donald Trump, probably who's somebody who's probably not at all connected to him. Certainly, let's say someone like me, he's almost certainly not going to do, if you do a short random walk around his neighbors, and you're probably not, the probability of landing up on me is very small. Smaller probably than it is when you look at the PageRank of the whole graph. So what's the claim? If you do a personal PageRank computation around every node you care about, now you've got vectors. These are good feature vectors for the same reason random walks were good feature vectors for deep walk and all these other things I've been talking about, right? And then if you could compress this thing, this vector, to a small number of dimensions, you have a perfectly fine, embedding. Any questions about that? That should make basic sense if you understand what I'm talking about here. Again, how could you project? You could do the random projection thing if you want. You could do any one of a number of different things. Any questions about that? Okay. Then the final piece of magic, because we were talking about this thing as being, what you call it, wanting it to be incremental for graphs that change, the add nodes, delete nodes, things like that, add edges. There are incremental ways to try to compute the PageRank vector. You'd like to add another edge. What does that change for the probability? If I add one edge to the graph, what vertices will I get closer to? What vertices will I get further? Will I be more likely to end up on? What ones will I be less likely to end up on? In principle, if you combine these things, you get an approach that will give you a time-varying embedding for the nodes you care about in a reasonable way, provided the nodes you care about are not that many, even if the graph is very, very big. Okay? And that's kind of why this is something to think about if you have dynamic graphs. Any questions about that? Okay? Yeah. You.
You mentioned earlier that...
Oh, sorry. Okay.
When you retrain, that the new embeddings don't necessarily represent the same features as they did earlier. Is that different here when you add an edge or add a node to the network?
Well, remember, what are the features here? This is the personal PageRank vector. This is telling me for every node, what's the probability I land at? If you start walking from me, you're going to go there. Now, the names of these nodes are still the same as before. So the features should be comparable. They should change, the weight values should change when I add an edge. But the feature dimensions are comparable as I was before. So I don't have this problem of needing to kind of retrain because the dimensions have, the names of the dimensions mean something different. Okay? And so that's a good, that's a win on this side. Any questions? Okay, good, man. Okay, let me get out of here. Now, there is this whole field of graph convolutional networks, graph neural networks. How many people know anything about those? Seeing a small number of people, this is good. So I've been talking here about graph embedding methods, deep walk and stuff like that. Deep walk is near and dear to my heart. It was one of the first of these kind of methods. But one thing is that once people realized that there were ways to take graphs and stick graphs into some kind of a machine learning model, people start developing better and more sophisticated approaches. There are these things called graph convolutional networks that are pretty important. Now, what are they, and how do they differ from what I was telling you about so far? Well, one, they are typically trained on supervised tasks. Okay? So I live in a world where I would like to take Wikipedia and turn the network into features and use it in many places. Remember, I come from the word embedding people. I wanted to come up with a feature vector for every word in a language so I could do different things with it, right? My features are now task independent. They were learned in an unsupervised way. Often, you have tasks where you don't really care about doing something generic. You care about building a model that uses the technique for your job. One of you at one point was interested in finding wilderness areas. I don't remember who my wilderness person was. But somehow they cared about taking, a graph or a map and identifying which places are wilderness. And if you want something to predict this, well, you now have a specific task, okay? Maybe you have features associated with certain nodes. Like in certain nodes, you know that they're trees. And in certain nodes, you know there are wild animals. Okay, and there's some properties that you know about some of these things. And you'd like to build a machine learning model that takes advantage of the labels that you have and any other properties and uses the network in a learned way. You also have examples. You know, good neighborhood in Manhattan, not a wilderness area. Okay? You know, someplace near the North Pole, wilderness area. Bad neighborhood in Manhattan, well, maybe a little more wilderness than before, but still maybe not wilderness, okay? Training a model based on those supervised things, that is what graph convolutional networks are good for, okay? And that's a little different than what the embeddings are, okay? Any questions about that? The other thing that is true about the graph convolutional networks, what they produce at the end is a procedure, a function that, given the neighbors of a vertex, produces an embedding for that vertex. So these kind of networks, if a graph changes, okay, if you add an edge or delete an edge, you could now just run your previously trained graph neural network on this new neighborhood and get a different representation for it, okay? So some of the dynamic problems become, you know, this is an approach that kind of, you can add new vertices, you can change neighborhoods, and within reason, you don't have to retrain the embedding on. Okay, and so that's a good thing a good thing. So graph neural networks are good things. Not complaining about them. They're obviously good things. Again, in my world, though, I'm often interested in embeddings, permanent feature vectors, more than I'm interested in a task-specific model. That may or may not be the case with you guys, but so you should know about these things. Any questions? And if you want to learn about this world, there is a book there. Now this is mature enough area. There's a book on graph representation learning. This kind of covers both graph embeddings and you know, these graph neural networks. Any questions about these? Okay, good. Let's see where we are time-wise. Okay, again, there's more that I can talk about with graph networks. There are other ways of using these graph embeddings that are kind of interesting. Sometimes you'd like a representation for a particular part of a subgraph. You have a representation for each vertex. How do you figure out what a subgraph means? Maybe you would average the vertices, the embeddings on a dimension-wise basis of all the vertices in the subgraph you care about. Another idea is sometimes before you train the graph embedding, maybe if you know there's subgraphs you care about, you can add a new node to represent that subgraph and connect it to all the vertices that it cares about. The embedding of this vertex will hopefully be a representative of the entire subgraph. Any questions about that? Okay. Any questions? So getting back to these convolutional networks, what is the big picture idea here? Okay. If you know about image convolutions, okay, and you know what a convolution in an image is, typically it is some kind of a weighted average over a window. That is what I picture a convolution as being. Maybe here you have an image, you have some kind of a weighted average of the points in a 3x3 window, and that gives you a value for, let's say, the central pixel in this window. These convolutional networks slide that window over the full image and gives you kind of a value for the center pixel where every window is. Okay? And if you then do this over the convolution on, again, on these newly weighted things, this gives you the effect of a bigger window. Let's just think about it. If we ran, here we had a 4 by 4 grid. When we finished this thing, there were 2 by 2 windows for it. If we now did a convolution on the part of the graph centered in these 4 things, that's going to take information from the whole graph. So just like in deep walk in some sense, when you do a random walk or you do a breadth first search, you're going to find all paths of particular length. Okay? What these graph neural networks do is basically you're training some kind of a function that will take the weights and labels of a particular subset of vertices, compute some representation that you're going to pass on to the vertex ahead. And the hope is that by training on a task-specific thing, you're going to come up with a good way to digest the information from a neighborhood, to pass the relevant information up ahead as an embedding. Okay? And this is the kind of thing that these graph convolutional networks do. I don't really want to talk about them too much, but if you have a world where you have a specific network, you have information, not just connectivity, and you only care about doing one thing, these graph convolutional networks are very good things. Any questions about that? Going once, twice, okay, fine. So what I'd like to talk about for the rest of my time, let me make sure I've got this time right. We've been talking now for, I believe, 50 minutes. That means 25 minutes, am I right? More or less. Okay, basically, I think, am I right there? Somebody nod or hold it up. 30, okay, that's right, but 35 minutes. Okay, good. Okay, I understand this now. Good. Okay, so what can you do with my embeddings? Again, what have I been spending the last 2 classes talking about? I've talked about how you can train on either text to get representations of tokens or networks to get representations on words. And what can you do with them? And one thing you could do is just take these things as feature vectors and pump them into your favorite machine learning model, be it regression or SVMs or whatever your favorite technique for taking a bunch of numerical features and producing your answer. But there's another type of model that I happen to like, okay, that I think is under-respected in the data science world, which are based on nearest neighbor models, okay? What is the idea of a nearest neighbor model? Suppose you have, you're wanting to build, let's say, a classifier. That's usually the way to think about it. Again, we had this guy who wanted to know wilderness area from non-wilderness area. How is he going to determine whether or not Brooklyn, okay, I'm from New York, you guys have heard of Brooklyn? This much you understand. Is Brooklyn a wilderness area? How would you tell? Well, one argument would be you build an embedding for all different kinds of areas, okay, and now you have a numerical vector representing what Brooklyn is. And what if you now say, have a bunch of examples of things that are wilderness areas and that are not wilderness areas? Okay, North Pole, wilderness. Yellowstone National Park, wilderness. Manhattan, not wilderness, right? And you now ask yourself, given my vector, which is it closer to? Okay? And if I have all my vectors out here, I would say what vector is most similar, closest to, the vector of something I have a label for. In this case, we would hopefully find Brooklyn is most similar to Manhattan, and Manhattan is not wilderness. And based on that idea, you can now have a classifier to tell whether something is a, for wilderness classification or not. And the same principle obviously will hold for any two-label classification problem. Any questions about that? If there's any questions about this, this is a good thing to make sure you understand, because this is a useful, simple technique. I always find in data science, there's questions of whether you need to be really smart or just avoid doing stupid things. I personally think in data science is a field where, in some fields, you need to make sure you do really smart things. I imagine particle physicists or string theorists need to be smart. Data scientists need to avoid doing stupid things, okay, is what I think. And that there's an art to that. That's not a small accomplishment, okay? To do that, it's good to have things that are simple, that you understand, methods that make sense to you. It's good to have things that are interpretable, that you can tell whether you're doing something right or not, okay? And it's good to have something that is nonlinear, because the simplest thing is linear regression, and there's limits to how complicated models are like that. When you have anyway, question. I thought it was a question. Yeah.
Yeah, small question. So does this mean that closer to the boundary you are, the more likely it is to be more forest than city in this case?
Okay, so what is the boundary? Okay, so maybe I should talk about this picture a little bit more. So what is this picture? This picture is an example of what you would love to have happen in a nearest neighbor type of thing, where you have red examples and blue examples. Those are your two classes. Red could be wilderness, blue could be non-wilderness, okay? And this is a two-dimensional feature space. Ideally, if you're working with my embeddings, your feature space might be 100 dimensions or 200 dimensions or something like that. But this is a two-dimensional thing. And the question now is, how confident are you in your classification? What's the way to interpret something like this? And it should be the case that in some sense, there is, in a nice picture like this, there is a boundary between the red points and the blue points. If you want to now know whether a new embedding is going to be labeled red or blue, you basically ask yourself, which side of the boundary is it on? And what do you hope? You're hoping, I think, not that you're close to the boundary, but you're hoping you're far from the boundary, okay? So if you view the nearest neighbor classification as a boundary issue, which is what I gather the question was about, you actually want to say, what is the bluest point there is? I would say over here. This is so blue, it's unbelievable, right? And if, trouble. And what's this? This is as red as it can be. So when you think of it in terms of a boundary, you probably want to think of it in terms of distance from the boundary as good. But there's a complication here, okay? This was a nearest neighbor classification, more than just a boundary classification, right? Is this the point that I'm most happy with? This looks so unbelievably blue. But am I going to be confident about whether, if I have a point here, that this is blue? I don't know if you guys can, can you see my? You used to be able to see this, didn't you? At one point you were able to see my mouse, right? Or it's disappeared years ago, no one remembers my mouse. Okay? Let's come over here. This point is far from the boundary. That looks great, right? Is this point, am I most confident that this point is blue? Some of you are nodding yes. I'm saying I don't know. Why? Because if you look at it, I have no training examples near here. This is actually one. What am I confident about this? I'm confident this guy is weird. Okay, he's unlike anything that I've ever seen before. Okay? So when it comes to nearest neighbor classification, I'd like to, I guess, be far from the boundary, but I'd more like to be near points that are really there. Okay, that may be, I think this is the interesting part of, I think, your question. I think I want to be here to be called blue, because I've got 5 or 6 guys around me, and they are all blue. Does everybody get that? Okay, so that's probably the right way to think about classification in this nearest neighbor world. Any other questions about it? So in order to do this nearest neighbors computations, you have to be worry about computing distances. Okay, that's kind of the hard, what's hard about nearest neighbor classification? If everything is being represented by an embedding, then what do I want to do? I want to compute the distance between two embeddings. Okay? And how do I compute the distance? Well, there are many, many things that look like distances. And, there has to be a little bit careful here. The distances that you and I are really familiar with in the world we live in, okay, have certain mathematical properties, okay? They're distance metrics. What is true about a distance metric? The distance between any two things is always greater than 0, greater than or equal to 0, right? I can't have negative distance from me to you. The distance between me and you is 0 only if we're the same. That's something that makes sense in distances. Distances are a symmetric thing, okay? The distance from me to you is the same as from you to me. And they observe the triangle inequality. The distance from me to you as the crow flies is always less than or equal to the distance from me to you plus the distance from you to him. Okay? Any questions? This is what we think distances should be. Okay? And this we understand. That said, many of the things that that data science people will think about as similarity-like things are not distance metrics. This is the first thing to kind of get cultured about. Okay? We talked about and we'll talk about cosine similarity. Okay, the cosine similarity, we'll talk about where that comes from. But you guys know enough trigonometry to know that cosines can go from 1 to -1, right? Now, that's not always greater than 0, is it? Okay? Correlation coefficients are usually a good measure of similarity. If I have 2 high-dimensional vectors, let's say this, I might want to think about the correlation coefficient between the dimensions. If I have 2 vectors, when one dimension is high, if the other one should be high. If when one is high, the other is always high, and when one is low, the other one is low. The correlation is going to be high. That's good. That probably means similar. But again, correlations go from -1 to 1. Some mutual information measures. I think we did talk about pointwise mutual information back when we were talking about embedding. That's not symmetric. Certain things about that we think of as distances are not necessarily obeying the triangle inequality. Suppose we say the distance between 2 places is the price of its cheapest airfare from one place to the other. Is the cheapest airfare from city A to city B always if you fly directly from A to B? No, it's often if you go out to Sheboygan, some weird intermediate step. It might be the sum of those 2 legs are less than the cheapest airfare. So recognizing that some distance scores obey metric properties, some don't obey metric properties is a thing to know about. And to realize that when you use something that doesn't obey metric properties, it doesn't mean you're a bad person. But it may mean that in certain contexts, you should make sure you really understand what the distances are being made and how they're being used. Because if you're using them in the wrong way, then sometimes weird things can happen. Any questions about what distances mean? When you're comparing, we have been talking about embeddings, okay? Embeddings we think of as points in higher dimension. There is sometimes a question of should we interpret our embeddings as being points in space or interpreting them as vectors. What is a vector? A vector, as far as I'm concerned, is a unit vector is always of length, the same length, okay? If it's of length 1, it's kind of like now this converts points in space to points on the surface of a sphere. And if you were outside the sphere, you got plopped down in the direction of the origin to where you hit the sphere. If you were inside the sphere, you continued moving away from the origin till you hit it. Okay? Are you better off working with the embedding, the raw embedding, or are you better off working with unit vectors that you form from the embedding? Okay? The answer, as in most things in life, is probably it depends. Okay? But when you think about measures like cosine distance, implicitly you're thinking about these things as vectors. When you are thinking about things by Euclidean distance or something like that, an LK norm, you are thinking about them by a geometric distance. Okay? And sometimes one is better than the other for computing similarity. Any questions about that? Okay, good. Now, that said, the cosine similarity is a good thing. Where does it come from? It comes from basically the idea of dot products. When you multiply two matrices, you're dotting a row with a column vector. You're getting a number. If you have a big dot product, it means that kind of the things were in sync. A big number times a big number is a big number. A positive number times a positive number is a positive number. A negative number times a negative number is a positive number. When they're in sync, the dot product gets big. When these vectors are kind of not in sync, the big positive things cancel the negative things, you expect to get something that is a small dot product. So what is the idea of cosine similarity? If you remember your linear algebra, if you have two vectors A and B, the cosine of the angle between A and B is the dot product of the vector A and the vector B divided by the size of the length of the two vectors. Okay? So if they are unit vectors, if you did project them to a circle, then then the vector lengths are 1, and it's only basically the cosine similarity essentially reduces to the dot product. Any questions about that? As you've probably seen, this is why it works. Again, dot products are a lot like correlation coefficients. And they sometimes make sense when you're working with embeddings because these are high-dimensional things. Correlations between high-dimensional things, the higher the dimension, the more the correlation actually tends to mean. Okay? And weird things sometimes happen geometrically in high dimensions. Any questions? Okay, good. Now, the geometric notion of distance that you learned back in high school was the Euclidean distance. okay? And what was the Euclidean distance? If you have two d-dimensional points, what was the Euclidean distance? It was given the ith coordinate of x minus the ith coordinate of y. Take the absolute value of that and square it, and sum this up over all dimensions, and then take the square root of it. That was the Euclidean notion of distance. Any questions? Now you may say, well, I don't know if I need the absolute value here, but I'm going to want it there for a reason. Okay? Any questions? Okay? Now, this you've seen for a long time. You know what Euclidean distance is. Does anybody know why you take the square in computing distance and the square root? Okay? Does anyone know why you do that?
Pythagoras?
What?
Pythagoras?
I didn't hear that.
Pythagoras?
Pythagoras, okay? Pythagoras said so, okay? So Pythagoras liked the Pythagorean theorem, okay? Probably liked it more when they named it after him, okay? But what the Pythagorean theorem works according to this. But notice that it turns out that while the Euclidean thing gives you a distance metric, there is nothing in the world about the twos there that makes a difference, okay? We talked about the properties that distance metrics have. You know, the fact that they're symmetric, the fact that they're always greater than 0, the fact that they obey the triangle inequality. The interesting thing is if you replace that 2 by k, you come up with a different distance metric for every distance value of k that you consider, okay? And so when you're trying to compute the distance between embeddings, there's no real law that says you have to stick to k equals 2. Pythagoras isn't looking, okay? He isn't watching what you're doing, right? And different k, if you think about it, what happens when you use different k? Okay? For k equals 1, what is happening? You're taking the 1 over 1, the 1th root of something. What is the 1th root of something? Something. Okay? Here you're summing up, okay, but summing up the absolute values? Well, that's sort of, instead of summing the squares of the difference, you're summing the absolute differences. Okay? For k equals 1, you get something called the Manhattan distance between 2 points. Why is it called the Manhattan distance? Well, in Manhattan, you have city blocks, you have buildings in blocks, so you can't take shortcuts. If I am 10 blocks north and 10 blocks west of my goal, how far do I have to walk? I have to walk 10 plus 10, 20 units, right? Pythagoras would have said, no, 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 you walk the square root of 20 units, right? But Pythagoras would have had to fly through buildings, okay? So if you have k equals infinity, what does this mean? You're taking every dimension, you're raising it to the infinitieth power, and you're then taking the infinitieth root of it. What does that mean? Well, big numbers, when you raise them to big powers, become very, very big numbers. And the biggest difference when you raise it to a huge power is going to dominate all the other things. So for k equals infinity, the distance is going to be, which is the dimension where there is the biggest difference between the two things. Manhattan was the sum of the differences. The k infinity norm would be the biggest difference between them. Okay? Which is the right k for your application? It depends, okay? But there's no reason why this shouldn't be an experiment that you would want to play with if you're using a nearest neighbor thing. There's a trade-off between whether you're caring about all dimensions being equal, or if how much one big deviation counts. Okay, that's kind of the issue with you. And that basically says the same thing. So when you say, when you think in terms of these different LK norms, recognize that circles have different shapes depending upon what K is. For K equals 2, Pythagoras' circle is round, okay? Maybe we like round circles, right? Now, what about in Manhattan? What does a circle look like in Manhattan? Well, a circle is all the points that are the same distance as you, right? And if your distance is defined by the sum of the deviations, you get a, a diamond-shaped circle. If you have L infinity norm, what kind of a circle do you have? Well, it's the biggest difference. What's the, over here, all of these points are 1 unit from that circle. So everybody see that the circle in L infinity norm is a square. Circuit at L1 is a diamond. In between, it's kind of a squared off circle type of thing. Okay? But again, different neighbors will be closer depending upon what your metric is, and some may be one that you care about. Any questions? Okay, so that I think you believe. What else can I say is interesting about nearest neighbor methods, as I see my time is winding down? What can you do with nearest neighbor methods? Well, what if you wanted to do classification? This much I think I told you about. You find the nearest neighbor and take the label of that nearest neighbor. That much you understand. The other big machine learning thing you want to do sometimes is regression. You want to come up with a value for what is the prediction of something is. If you want to estimate how rich somebody is, let's think about this. If I want to figure out how rich you are, you over there, what would be a way I could do that? Well, I could take all your variables about you, your height, your weight, how long you were educated, and build a linear regression model to predict it. Or I could say, what are the 10 nearest people I have who are closest to you in data space? And average their salaries. Everybody see that that gives me an estimate for how rich this guy is. Okay? So understand that nearest neighbor methods can be used for regression as well as classification. For anything you do machine learning on in a normal way, there are simple ways of doing that with nearest neighbor methods. Any questions? Good. Now with classification, this idea of how to make these things more robust, there's a question of if I want to come up with a classifier to separate red from blue, okay? I could just take the label of the closest neighbor, or I could instead say, let's look at the k nearest neighbors and take maybe the majority of the labels from this. And this turns out to be a very good idea. Here, this is an example of a gender classifier we built from some data set where we knew people's height and weight, and we wanted to tell, are they male or female? Okay? Generally speaking, at least where I come from, women tend to be shorter than men, and they tend to weigh less than men. Okay? So you should be able to do some kind of classification like this. In the data set we had, if we looked at, for k equals 1, where we're only going to make our decision based on the nearest example in our training data, your decision boundary looked like this. And this is a pretty weirdly shaped decision boundary. What is the thing here? Why is there suddenly this pink I guess I'll call it fingers sticking up in my data set. What is this? There is one point that's pretty far from a lot of other points that happens to be, I guess in this one, a female point, right? And the reason this region is all pink is because of that one training example. Does everybody see that? And this is now a problem, because any point that's up here, okay, there's not very much data, there's not very much about it, okay? It is clearly overfitting the training examples. So everybody kind of get that idea? If you now build an example where you now say, okay, let's take 3 nearest neighbors and take the majority label, my boundary gets much simpler than it was before. But there's still weird things happen. It happens over here. This segment here is because this point and I gather this point all happen to be, more points. All those points out there are closer to these two than they are to any of the blue. As you raise K, you get smoother and smoother decision boundaries. Normally, smooth decision boundaries are good, okay? And, there are going to be some misclassifications from the training stuff and stuff like that. But generally speaking, the higher you raise K, the smoother your boundary is going to be. If you make K too big, it's going to be a beautifully smooth boundary that doesn't predict very well. But if you have the right value of K, you get a nice nonlinear boundary, okay? But, and that is reasonably robust. Any questions about that? So these nearest neighbor methods, I think, are very good things, and I want to encourage you guys to keep using them. One philosophical reason for considering nearest neighbor methods on embeddings that I think are important is that there exist many intellectual fields where, or many parts of the world where people do think in terms of analogies. Now, in computer science, people usually don't seem to think in terms of analogies. But in law, when you want to say who should win this legal case, what is it that lawyers do, at least in the United States, and probably it's true where you guys are too? They find some previous case that they say is very, very close to this case, and say, in this case, they hung the defendant, okay? So you got to hang the guy now. That's kind of what an analogy reasoning is. That kind of reasoning from precedents, that's actually a nearest neighbor idea, isn't it? In medicine, what does your doctor do? You come in with a tongue that's purple and your hair's falling out and you're walking with a limp, and the doctor, you've got to say, doctor, what do you do with me? What's the doctor going to do? If you have an experienced doctor, they're going to think back and they said, have I ever seen a patient who had a purple tongue with hair falling out and walked with a limp? And yeah, there was this guy 20 years ago. What did I do for him? Well, the guy died, so you're going to die, okay? Does everybody see that you've got that kind of reasoning? And nearest neighbor methods, I think, are good for reasons like that. And maybe I'm beating this to death a little bit, but I think you guys understand that. Any questions or comments about it? The one bad thing about nearest neighbor methods is actually, it turns out the training time for models on nearest neighboring methods are fabulous. There's no training time at all. If I want to come up with a classifier, what do? I did no training. I just take my points, and when I need to classify something, I go through and compute the distance against each one. So training times are fast, but the actual, I guess, inference times, finding what the nearest neighbor is, often involves searching through all the points in a kind of brute force manner. if you have a lot of examples and you're trying to find the nearest neighbor of them. It's not that the training becomes hard, but the inference becomes hard. Does everybody kind of get that idea? Okay. And if you're going to do that, okay, then you need to use some kind of a more sophisticated, there are some more sophisticated ways to help find nearest neighbors, okay, that work well in modest dimensional spaces. One of them is a data structure called a Voronoi diagram. I don't know, have anybody ever heard of Voronoi diagrams? A couple of people. Oh, good, okay. You could kind of think of taking your points and building a structure where you carve space into regions, where the region around a point, and I guess it's funny, I'm moving my point here, and that's probably bad. The region around a point are all the points is the entire space where this is the closest neighbor to it. So determining the nearest neighbor of a point reduces to what region are you in. And so if you can take your points and build a Voronoi diagram and quickly find what cell it is, it's quickly, it gives you a way to, to find the nearest neighbor quickly. Good thing is this can be fast. Bad thing is this is only in low dimensions, ideally 2 dimensions, whereas we've been talking about dimensional spaces that are much higher. There exist other algorithms that are more practical in higher number of dimensions, okay? Using data structures called things like KD trees or ball trees. And my students, when I ask them to find nearest neighbors of things, they tend to use in Python a data structure called a ball tree that they seem to find in one of the fundamental libraries. And this basically carves up space into regions that are not these complicated regions, but are fairly regular things. And by walking down the tree, you find nearby points relatively quickly. Okay? Any questions about that? This much I think now you guys should see. Okay. Given that, I think I am going to, at this point, stop. I can tell people's energy is waning. Okay. Any questions about this idea of, we've gone through the story of what is a embedding. We've gone through how you can take your data and construct embeddings for things, these vector representations. And we've talked about what you can do with these vector representations that include relatively simple things like finding nearest neighbors and stuff like that. And I think these are kind of tools that are pretty fundamental. Again, these are the kind of tools I like to talk about in my book, okay? So if any of you are interested in data science, I do encourage people read this. And I'll take any final questions, or if not, send you off to the world. Okay, any questions? Okay, if not, thanks for your attention, and I'm here. I'll be here for a few minutes if you guys want to chat, but if not, thanks for your attention, and it's been fun talking to you.